So let's begin. Good afternoon, everyone. I'm Srishti Siddharth. I'm a PhD student associated with the Center for Systems and Control at IIT Bombay, and I'm also the TA for this course, W98. So let me just check something before we begin. Mm, So let's look at the overview of week 5. Yes, that's true. So in any of the control design, you first have to actually select a lab in a function, and all the analysis after that depends on it. So let's begin. Yeah, yeah, yeah. They are. So if the cost function is, it is actually positive definitive. It's usually quadratic, so that works as well. Yeah. Yes, yes, yeah, that's true. Yes, we don't need it to be convex. So we looked at diagonalization of the state space system. X dot equals ax plus bu, then the output equation. Then we look at the state transition matrix, or in other terms, the matrix exponential for LTI systems. Solution of homogeneous system x dot equals ax. Homogeneous or autonomous. And then finally the whole system, solution of the non-homogeneous system. Some other names are autonomous, free response, or the zero input response. And these are non-autonomous. All right, so let's look at the first section, diagonalization of the state space system. Yeah, yes. So it's basically that, and yeah. So in that case, we just focus on the any particular matrix, but in this case, we have the state matrix. So we have its eigenvalues, and so we have its modal matrix. So we have those eigenvectors arranged in a column, and we actually use that as a transformation to make it a diagonal system. For example, we have some n states. And let's consider for now that n is 2. So the A matrix is simply A11, A12, A21, A22. So this is for the state X. And if we want some transformation which takes it to some states Y, in that case, we want the matrix to be diagonal. So zeros here and some non-zero entries here. So we want these non-zero entries to be eigenvalues of the system. And in that case, you can also see that AD inverse is simply 1 over lambda 1, 1 over lambda 2. See, in case lambda 1, lambda 2 are not zero. Alright, so this means that there is some transformation between these two states. Let's write them as y equals p of x. And we want to be able to switch between x and y. So this means that p should be invertible or p inverse should exist. Or the determinant of p should be non-zero. So this would help us to construct the original state that we had for the system. This is simply p inverse y. And now if we just differentiate both the sides, this must be ax plus bu, right? Because this is x dot. And we're considering that p inverse at the moment is time independent. Simply means this is P inverse y dot equals ax plus bu plus bv. And we can rewrite x as P inverse y. So this is the new state matrix, which is diagonal if we use the modal matrix P. And this is the new input matrix. Just note that we use this kind of transformation x equals, just a second. Yeah. So instead of this one, usually we use x equals py. Right. These are the old states, and these one are new. So in this case, this would be, for example, maybe switched P inverse AP. So once you fix this, you just need to rederive this equation so you're sure whether the new matrix is PAP inverse or P inverse AP. That's always a source of confusion, so just note this. Okay, so let's look at a question. Yes. So it's also called a similarity transformation. You preserve the properties of the system, right? The eigenvalues. Sorry, what? Yeah, these are the eigenvalues, right? So these are these contain the spectrum frequencies or F if you want to write it. Is that what you meant? So let's look at a matrix. So it's A minus 4, 1, 0, 0, minus 3, 1, 0, 0, minus 2. Alright, so to get the P matrix, you need the eigenvalues and the corresponding eigenvectors. So for that, let's write down A minus lambda I. That is simply minus lambda on the diagonals. Rest of the entries remain the same. So this is, and the eigenvalues are just the root of this characteristic equation. So let's see. You can just expand along this column. So it's minus 4 minus lambda, and this equals 0. This means lambda is minus 2, minus 3, and minus 4. Okay, so this is the case of distinct eigenvalues. We can easily find the eigenvectors. Let's start that. So for lambda equals minus 2, a minus lambda I v equals 0. This means that we have minus 2, minus 1, 0. v1, v2, v3 equals 0. This is just a row of zeros. That means we cannot determine v3 independently. So v3 is, let's say, some scalar k minus v2 plus v3 equals 0, which just implies that this is also some scalar. And then from the first equation, we have minus 2v1 plus v2 equals 0. So the eigenvector looks like k times half 1, 1. So we just usually take k equals 1, and in that case v is half 1. We can just repeat the process for the other two eigenvalues. Let's do that quickly. For lambda equals minus 3, minus 1, 0, and plus 1, and 1, 0, 0, 1, 0, 0. Alright, so these two equations are the same. Let's simply say that v3 is 0. Alright, so we have to choose either v1 or v2. So let's see, minus v1 plus v2 equals 0. v1 equals v2 equals some constant k. So the eigenvector is simply 1, 1, 0. Last case is lambda equals minus 4. So that case is 0, 1, and 2. 0, 0, 1, 0, 0. v1, v2, v3. So in this case, you can just easily observe that we'll have to assume a value of v1, because we don't have it. So let's see. From the third equation, it's v3 equals 0. From the second equation, it's v2 plus v3 equals 0, which is simply v2 equals 0. And the first equation also implies this. So v is in k, 0, and 0. So the transformation matrix in this case is we have to arrange the eigenvectors of lambda equals minus 2, minus 10, minus 4 in a column. So I'm going to write this down as v1, v2, v3, where v1 is for lambda equals minus 2, lambda equals minus 3, and lambda equals minus 4. So I'm just going to write this down for constants 1. So k equals 1 in each of them. So let's check. This is, okay, let's see this. 1, 1, 0, 1, 0, 0. And let's see, to actually simplify the calculations, let's consider k equals 2 in this case. So that would simply mean it's 1, 2, 2. So after writing down the P matrix, the first check that we should do is P invertible. So let's check the determinant. This is 0 minus 1 times 0 plus 1 minus 2. Okay. So P is invertible. This means that we can use this as a transformation to diagonalize the system. Alright, let's see if the new A matrix, let's see it's A tilde. This is P inverse A. Now our job is to find P inverse. So again, we can do this by various methods. Uh, let's see if we can do this by the cofactor and joint of a matrix. I'm just going to write this down directly. You can check, or you can also check using MATLAB. So joint of P is 0, 0, minus 2, 0, minus 2, 2, minus 1, minus 2, minus 1. And the cofactor matrix is simply 0, 0, minus 1, 0, minus 2, minus, minus 2, 2, and minus 1. So P inverse is simply 1 upon determinant, which is minus 2, and the transpose of the cofactor matrix. Okay, so after substituting this in A tilde, we have, you can actually check this. This comes out to be minus 2, minus 3, minus 4. So this is a choice that we have actually written down the columns starting from minus 2, minus 3, and minus 4. If you switch any of these, just make sure that P is still invertible. And in that case, you would get maybe something like, if the minus 3 eigenvector was the first one, this would be minus 3, minus 2, minus 4. This is also completely fine. Or any other choice. Yeah, I think I have it somewhere. Let's see if we have it right now. Okay. If not, then I'll actually find out an example somewhere. So what's the first one? Okay. So now we have the double integrator, the simple pendulum equation. This is d squared theta by dt squared equals et. So this is second order. We need two states to define this. So this also is the equation for the planar pendulum, where at rest it's in the straight position and at some angle theta is here. So it's just more constants on either side. So the first question is, formulate the state space model. Okay, so let's consider the first state x1 as theta, x2 as theta dot. So this means x1 dot x2 dot is going to be some matrix times x1 x2 plus b. So this is 0 1 and then it's 0 0 and just 1. Okay. So this is the A matrix and this is B. Let's look at some transformation, parity transformation. It's as old some old states equal transformation matrix times new state. So let's say if P is 1 0 1 1, this form under the class of transformation matrices. So what do we need? We need to first check if P is invertible and then find out if we have some A bar and B bar and if A bar is diagonal. Just 1 second. Okay. So determinant of P is simply 1. Then let's see. A bar is P inverse AP. Inverse is simply determinant times 1 0 and minus 1. Okay. So A bar is going to be 1 0 minus 1 1. Then A is 0 1 0 0 1 0 1 1. Okay, so let's just calculate this quickly. This is 1. This is also 1 0 0. And then we have, so you can see that this is actually not diagonal. And of course, you can find some B bar equals P inverse B, which is 1 0 1 1 times 0 1. Okay. So usually we actually write down the vectors or the eigenvectors corresponding to eigenvalues. So what's the problem in this case? The problem is that we have repeated poles on the imaginary axis, right? Those are the eigenvalues of the pendulum or a double integrator like this one. Okay. So that's the next part. So that the two eigenvalues. Of the system matrices. Just a second. Fine. Okay, show that the eigenvalues of the system matrices of the two state space are equal. So what are the state space matrices? A is 0, 1, 0, 0. And let's say another one, A bar is 1, 1, minus 1, minus 1. Okay, so this is from where, and this was the original A matrix. So what we want to actually talk about is that the P considered above is a similarity transformation. So all similarity transformations do not need to actually diagonalize the system. There are some which do not diagonalize. For example, we get A bar here, but still the system has same eigenvalues. The two systems have same eigenvalues. Diagonalize. The transformed system has the same eigenvalues. So let's write this as A and A bar. So let's check this. So the determinant of A minus lambda I is 0. So simply lambda square equals 0. Repeated both at the origin. And for this case, so we have 1 minus lambda minus 1 minus lambda. Minus. Let's see. Plus lambda square plus 1 equals 0. Again, it is lambda square equals 0. So a similarity transformation always preserves the eigenvalue of the transform system. Right. So let's look at another matrix, which is the van der Waals matrix. So A is written as 0, 1, and then zeros. Then the 1 shifts to the right, zeros drop. Then 0, 0, 0. And then we have at the last row, it's minus alpha n, minus 1, till minus alpha 1. So if you recall from, I think, the first week's lecture, this is the CCF form. So if we have an A matrix like this, and if all the eigenvalues till lambda n are distinct, these are distinct eigenvalues, then you can actually consider this as the transformation matrix P, which is invertible, and it's written as, so the first column is just a row, the first row is just a row of 1, then it's lambda 1, lambda 2 till lambda n, then the next one is lambda 1 square, lambda n square, so on till lambda 2 to the power minus 1. So this is also n by n. And if we use this similarity transformation, then P turns A, or let's say transforms A. into the Jordan canonical form. For distinct eigenvalues, it's lambda 1, lambda 2 till lambda n, all zeros here, all zeros here. So if we have a matrix, system matrix, which is already in the CCF form, so instead of finding the eigenvectors for each eigenvalues, what you can do is simply solve the characteristic equation, get the eigenvalues, substitute in this P, which just naturally transforms to the diagonal form. And this is only if we have distinct eigenvalues. Alright, so let's look at a question. So if x star equals 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6. Then that's x. Okay, let's just write this down as x. Plus 0, 0, 2 times 0. So first, notice that this is already in the CCF form, right? So this is 0, and this is the chain of integrators. This is minus alpha until minus alpha 1. So this is CCF. I is 1, 0, 0, x. Notice that this is not 1. So right now we're just talking about the CCF form of the A matrix. The system using a similarity transformation. Then find the modified system. So we just have to figure out what the eigenvalues are, and then we can substitute in the van der Waals matrix, this one. Okay. Lambda minus 6 minus lambda. Okay, so yeah, yes, yes. Yeah, the damped oscillation. So if you also have real part on the negative escape. This is lambda square plus 6 lambda plus 11 plus this equals 0. So let's see what the roots of this equation are. Let's check if lambda equals minus 1 is true. So mm, 1 plus 6. Yeah. So you can just put this common and figure out the rest of it. I'm going to write this down directly. 5 lambda plus 6 equals 0. So this is simple. Alright, so we have lambdas as minus 1, minus 2, minus 3. So these are distinct. We already know the diagonalized system would be this one. Okay, so the van der Monde matrix or the similarity transformation, this case is going to be 1, 1, 1. Three, and then 1, 4, and 9. So let's check if A equals P inverse AP. Sorry, A bar. Let's check this after this class. They should be equal. Yeah, for this one, right? Where is it? This similarity transformation. So if we have distinct eigenvalues, we already have a formula for the similarity transformation. Sorry? Yes, yes, it's a standard formula, right? Yeah. So that you don't have to find the eigenvectors for each time you have distinct eigenvalues. If it's complex, I'm not sure actually. Let me think. Mm, There are actually many cases. So if it's real and distinct, it's this one. If it's complex, then it's another matrix or another way to solve this. If there are repeated poles, then there is another method. I'll actually have to think about a source. I think that would be in any of the textbooks on control system. Like if I think there are some cases, right? So what they do is they write down this if A is some Rn by n, and if n are distinct, you can use this. If n are complex, then I think there is another method. I'll have to check this out, but um, yeah, I mean you cannot use this if n are complex, but I think you can still use that approach, right? A minus lambda I applied to V should be 0. In case lambda is some complex number, then V would also be complex, right? If it's a 3 by 3 matrix, you can actually solve for all the three components of V1, V2, V3. But again, this is only if we have complex eigenvalues and they do not repeat. If it's repeating, then there's going to be another procedure. There are a lot of maths. Okay. Yeah. Oh, yes, you can. You still can use this equation. This one. Hmm. Let's see. What has eigenvalues on the imaginary axis? Hmm. Yeah, yeah, that is true. One second. Let me think of some 2 by 2 matrix which has complex eigenvalues. this is no. I think it would be a trial and error process, right? We first have to figure out what A matrix should we choose. Um, yeah, that's fine. Mm, let's see. Let me just find some simplified A matrix and then we can go ahead. Uh, yeah, sorry. Yeah, I think there's a standard book. I think it's PC book. Sorry, it's smaller. I think it's a standard textbook in control. Um, Other than that, it's Ogata. Have you heard of that? I think you have, right? The book by Ogata. Yeah, I think so. Yeah. Modern control or something. Yeah. There is a book by Nice. I think it's all. Okay. Yeah. Optimal control in that case, I think there's a book, Optimal Control is in Skirk. Is one book by him. Another book is, you can actually get an online version of this one. This is available. Yeah, yeah, it is. It is. Yes, that's great. Yeah, that is, yeah. I think this would be in your library. You can check this one out. Kirk is a very standard textbook. Hmm. Okay, so after 15 minutes, we'll shift to that other call. Is that fine? Yeah. Okay. No, I have shared it in this chat box. Yeah, just copy this one because I think after the call ends, you cannot really access the messages. So it's in the top of. Okay, so let's see. Sorry. Okay. Okay, so I think you can. You do not have my email, so you can actually drop a message in that Q&A forum. I regularly check that as well. So if you, yeah, just one second. Let me just get a simple example. So I think complex eigenvalues can be when we consider an electrical circuit, and you can have A as inductors or capacitors, I think so. But anyway, so this is the simplest case, I think. 1 minus 1, 1 and 1. Uh, A minus lambda I is this, and the determinant should be 0. This is 1 plus lambda square minus 2 lambda plus n equals 0. Mm, all right. Now let's see, these are distinct, so it's simplified. So let's see if we can find the two eigenvectors. 1 plus I. This is I minus 1. Ah, okay. Yeah, it's usually the real part is negative, but okay, let's try this. I think now we just have two equations to solve, right? First one is I v1 minus v2 equals 0 minus I v2 equals 0. So 2 into I. Let's add this. Let's see. Just check if the calculations are correct. So v1 equals 0. Mm. We are actually not looking at 0 vector as an eigenvector, so this is not correct. See if we can find some other example. Which matrix is it? This one? V1 and V2 can be any complex numbers. No, this is a 2 by 1 vector. Yeah. Actually, there could be many, but right now this is not correct. So let me just check. It's like we have with real eigenvalues, right? It's some constants times some vectors. So you can have multiple eigenvectors. So the basic definition is, I think, EV equals lambda V, right? It's the same equation, but let's see. One V2, lambda is 1 plus R. Mm, okay. That's fine. We get the same equations, I think, but mm, so I think we have this one. Sorry, the one below this and this one. Let me check if we get the same one. Okay, so this was IV1 minus V2. This is fine. V1 minus IV2. Okay, so this one is different. See if we get a non-zero eigenvector. The two equations, let me rewrite this. IV1 minus V2 equals 0. IV2 equals 0. So it's times I is still get the zero vector. So no, I think we'll have to consider some other example here. Getting back to that zero vector. One second. That's not the eigenvector we want, right? Because that's always trivial. We want a non-zero vector v such that av equals lambda v. So v can never be a zero vector if it's an eigenvector. Yeah, it would be, yeah, it's trivially solved. Okay, yeah, an example, but it's a different matrix. So I don't know what happened with this one, but if he is 1, 2, let's see, minus 2 and 1, if we get some non-zero eigenvector for this one. So um, this is 1 minus lambda, this, minus 2 lambda plus 5 equals 0. So lambda is the same equation. Yeah, sorry, I think the call is going to be end in 1 minute, so let's shift to that other link. Yeah, yeah.